welcome once again. So last class we have covered the tutorial on continuous probability distribution, but we could not solve problems on all the distributions. We have only done some problems on normal distribution and log normal distribution. In today's class we will be seeing exponential distribution, problems on exponential distribution, problem on Gaussian distribution, and also again some more problems on normal distribution, because normal distribution is a very important distribution, not only from the reliability perspective, from in other application perspective as well. So directly coming to the problem, see the first question: the length of time for one individual to be served at a cafeteria is a random variable having an exponential distribution with a mean of 4 minutes. See, interesting. The length of time for one individual to be served in a cafeteria, it is a length of time that is the time that is in a random variable, and it is an exponential distribution with a mean of 4 minutes, meaning the time it takes for a person to be served, basically how much minute it takes for the person to be, that means we can say that is the rate of the event. Okay, so that the rate of the event, it is specifying that it is 4 minutes. Okay, what is the probability that a person is served in less than 3 minutes on at least 4 of the next 6 days? See the second part. What is the probability that a person is served in less than 3 minutes? That means we have to find out probability that if you are taking t as a random variable, t is less than equals to 3, probability of t is less than equals to 3, we need to find out the person is served in less than 3 minutes. Okay, on at least 4 of the next 6 days. 4 of the next 6 days, this directly implies a binomial distribution, as if there are 6 trials, out of 6 trials I need 4 success. Okay, 4 success, and what is the probability of success? My probability of success is this: a person is served in less than 3 minutes. This is my probability of success. 6 trials, out of 6 trials 4 success. In binomial distribution, what are the parameters? First is number of trials, number of success, probability of success. These are the 3 parameters to define a binomial distribution. So this is number 6 is the number of trials, 4 is the number of success, and that the person is served in less than 3 minutes, that is the probability of success. Now, how do I get the to find out the probability of success? Second part I understood is a binomial distribution. So how do I get the probability of success? That is what is the, that is a exponential distribution, isn't it? The time it takes for the first event to happen, time it takes for the bus to arrive, time it takes for the failure to happen, isn't it? Time it takes for the person to be served in a in a cafeteria. So these are the occurrence of an event. So that is the rate of an event. So this directly is an exponential distribution. So we know the formula for the exponential distribution. I mean, when I call it formula, I mean probability density function. I will not mention it again and again. When I am telling it the formula, it means the probability density function. So I know the expression for the probability density function. What is the exponential for exponential density function? It is 1 by beta, right? 1 by beta e to the power minus x by beta. This is my density function. So I need to find out what it is given, at least served in less than 3 minutes. That means I have to integrate it from 0 to 3 dx. This is my fx, which I have to integrate it from 0 to 3. Then I will get the value for probability of x less than equals to 3. Whether I tell it's less than equals to 3, or in very important thing, in continuous probability distribution, if I tell p of x 3 and p of x less than equals to 3, 2 are different things or same thing? 2 are same thing, because at equals to 3 probability is 0, right? Similarly, if I tell greater 3 or greater equals to 3, both are same thing. Okay. So y be the number of days a person is served in less than 3 minutes, that is the y be the number of success, what I told you. So I found the probability is 0.5273, probability of success. Now simple binomial distribution. Okay, simple binomial distribution, specifying the value. So this is the probability, this is the number of success, this is the number of trial. Simple put it in the probability distribution function of binomial, and we will get the value. Okay. Next question: the life in years of a certain type of electrical switch has an exponential distribution with an average life beta is equals to 2. Okay. The life in years of a certain type of electrical switch has an exponential distribution with an average life of beta is equals to 2. Here beta is specified, it is equals to 2. Life in years means the time it fails. Okay. So rate of failure is, that is beta is equals to 2. If 100 of this switch are installed in different system, say if 100 of this switch are installed in different system, what is the probability that at most 30 will fail during the first year? So I need to find out what is the probability that a switch will fail in 1 year during the first year. So from 0 to 1, what is the probability that a switch will fail in first year? That we will find it by exponential distribution. Then see the next portion, 100 of this switch are installed in different system. What is the probability that at most 30 will fail? At most 30. When 0 can fail, 1 can fail, 2 can fail, up to 30. It is again a binomial distribution where n is the total number of 100 is the total number of trials and 30 is the number of success, at most 30. So essentially it is a cumulative binomial distribution from 30 to 100. Now there is one thing which you need to know is that when the n is quite large, like here when n is quite large, then sometimes binomial distribution can a discrete distribution also can be estimated by approximated by a normal distribution. Mainly in case of binomial distribution, if the binomial distribution, if it takes a bell shape, binomial distribution definitely we will our graph will not be a curve, right? It will be either bar chart or it will be a histogram, whatever it is. So if we if it is in the form of a this sort of thing, so it forms what? Bell shaped, isn't it? So in the binomial distribution, if the curve is the resulting diagram, I should not a curve, the resulting diagram is in the form of a bell, if it gives a bell shape, then we can approximate binomial distribution by normal distribution. Why we will do that? The thing is that now see for this case, you have to find out for 100 is n is 100, our x is 30 and you have to find a cumulative value. And for cumulative value of 30 and n is equals to 100, if we have the table, if we have the corresponding table for that, for the corresponding probability, of course the probability is also important. For the probability, if we have the corresponding probability, if we can look it in the table, it is fine. But if probability in the table, we don't have the table for all possible values of probability and all possible values of n and x. So if the table is not there to calculate such a big number, it is a very trivial, it is not a very easy task. So in that case, if we can approximate it by binomial distribution, things becomes very easy. Our life becomes easy if we can approximate. That's the, and when we see if we approximate it, our value will not be significantly changed. Their value will change slightly, which it can be considered. So that's why in such cases we can approximate by normal distribution. Now here in case we will be approximating by normal distribution. So when is a normal distribution, again we need two parameters. What are the two parameters? The parameters are mu and sigma. So for normal distribution, what is mu? Mu is n into p, and what is sigma? Sigma is npq. Variance is npq. So to find out for normal distribution, we need mu and sigma square. Here mu and sigma square nothing is given, but here we will be able to find out the p, probability that it will fail during the first year. Using the exponential distribution, we will be able to find out, that will give my p. We have n is 100. So once I find my p, q is 1 minus p is q. So I got my mu, I got my sigma square, then I will be able to find out my, I will be able to find out the required probability using approximating by normal distribution. So you see how first we found out the probability using exponential distribution, probability density function exponential distribution, where beta is 2 is given. So this is how, this is the probability we got. So now we will be approximating using normal distribution. So what we took, mu is n into p, we found is this, then we found out the standard deviation, we found this, then we need to find out the z value corresponding to at most 30 fail. So it is, this is 0 and something, 30 means whatever value will come to for whatever value will come for 30, whatever z value. Now see, when we are trying to approximate using a discrete number, when you are trying to approximate by continuous variable, we'll have to consider as the what to say, it's near about value, like when 30, because probability at exactly 30 will be 0, right. So, and when we are considering a 30, that means it will be in a very small interval nearby 30. So, when it is given at most 30, it will fail at most 30. So, we cannot consider exactly at 30 here. See, here we have considered 30.5 instead of 30, because when we are approximating for continuous, we will have to take a closer interval near to 30. Okay. So, I have taken is 30.5 here. So, if in other cases, if it is specified that it is less than 30, then I would have considered, I wouldn't have considered 29, I would have considered 29.5. Okay. So, I found the z value here minus 1.81. Once I found the z value, then getting the probability, and just a matter of looking into the table, that is all. Okay. So, that is the minus 1.81, that is the value from the table, I got this. So, this is the probability. Okay. So, next, a component has a constant failure rate with mean time to failure of 500 hours. What is its reliability at 375 hours? Similar type of problem. Okay. So, here beta is given, it is 500 hours, mean time to failure, that is 500 hours. So, then we have to find out the reliability. This is again an exponential distribution. Exponential distribution, we know it is 1 by beta e to the power minus x by beta. Again, one more thing, the 1 by beta is also equals to lambda. We have seen that, isn't it? 1 by beta is nothing but is equals to lambda, we have already discussed. So, instead of writing that, we can also write, instead of writing lambda 1 by beta, we can also write lambda. So, when we try to find out the reliability of this, first we will have to find out f of t. So, f of t will be nothing but integration of the probability density function what we have. So, and once we integrate that, what we will get? We will get 1 minus lambda e to the power minus, 1 minus e to the power minus lambda t, not lambda is not there, e to the power minus lambda t. You can write it in terms of beta, or you can write it in terms of lambda, whatever it is. So, if this is f t, then what is my r t? What is my r t? R t will be just e to the power minus lambda t, or e to the power minus 1 by beta t, whatever. You may write in terms of lambda, you may write in terms of beta. So, that is all. Here it is given, I have written in terms of lambda. Fine. So, a component has a constant failure rate of 0.00225 per hour. Okay, failure rate of this much failure, 0.0025 failure per hour. See here, please notice the difference between this question and the previous question. It is given the component has a constant failure rate of 0.0025 per hour. That means 0.0025 failures per hour. Okay. If this is 0.0025 failures per hour, that means what will be my, then that means this is my lambda value, this is not beta value. That means if I consider beta will be equals to 1 by 0.0025, because this is considering 0.0025 per hour, 0.0025 failures per hour. When I consider beta is 1 failure per unit time. Okay. So, it will be beta is equal to 0.0025. Rather, I can say here it is specified, alpha is specified, lambda is specified. So, here lambda is equals to 0.0025. See the difference between the previous question. What was the previous question? As constant failure with mean time to failure of 500 hours. Mean time to failure means that is the time it has, time for the first failure, or the whatever the one failure has occurred, the time it has taken for the next failure to happen. So, there is within 500, that is the first failure that has happened. Okay. So, that is beta. See the difference between the alpha and beta here. So, here not alpha, lambda and beta here. So, this is lambda is given. So, directly we can find out the reliability is e to the power minus lambda t. Again, a component has a normal distribution of failure times with mean equals to 20 cycles, standard deviation is equal to 2 cycles. Find the reliability of the component at 19,000 cycles. I have given lots of question on reliability. Why? Mainly you will have an idea on reliability as well, plus you will be practicing more and more problems on different distribution. So when you talk of reliability, it's nothing, just you find out first you find out a cumulative. If I consider the variable, when we talk of reliability, the random variable we consider easily in terms of time, that is time to failure. Okay, so then if the t is my time to failure, then small f of t is my failure density function, then I get capital F of t. What does capital F of t implies? Capital F of t is the cumulative failure till time t, that means from minus infinity to t, that is the cumulative failure. So once I talk of cumulative failure, that is f of t from time infinity to t, that is the cumulative failure, then when what will be my reliability? Reliability will be simply 1 minus f of t. Okay. So that's just the difference between the f of t and r of t. 1 minus f of t is r of t. That's why I am telling that is the reliability of the component. Now when I am asking reliability of the component at 19,000 cycles. Okay, so that means first I have to find out what is the failure probability till 19,000 cycles. That is f of 19,000. Okay, so that means till 19,000. F of 19,000 means from minus infinity to 19,000. So it is a cumulative. So we can look it from the table, we can get the value, and whatever 1 minus of that will give the value, right? So it is these are the expression. What just for a quick recap, I have given you this is the failure density function for normal distribution. If we find out the cumulative, this is the value, and this is the value we'll look up in the table, that is the Z value. And for the Z value, Z is equals to minus 0.5. So corresponding to minus 0.5, we will get the value from the table, and what we get is 69.15. Okay. Okay. Similar type of question. 5% of certain grades of tires wear out before 25,000 miles. Another 5,000 of tires exceed 35,000 miles. Okay. Determine the tire reliability at 24,000 miles if the wear out is normally distributed. Okay, given the wear out is normally distributed. So first let me draw the normal distribution. What it is given? 5% of the certain tire wear out before 25,000, 5%. So 5% means always this 5% means the probability, that is means the area. So this is corresponds to 25,000 miles. So 5% wear out before 25,000 miles. Another 5% of tires exceed 35,000 miles. Exceed 5,000, exceed 35. So definitely it will be this side. Definitely it will be this side. Another exceed 35. So this side it is exceed, this side it is less. So this is 35,000. Okay. So what it is given? What is the probability corresponding to this value it is given? Probability corresponding to this value it is given. In earlier cases till now what we have solved, we did not know the probability corresponding to a particular Z value. Particular Z value we could find out. How? If the random variable was x minus mu by sigma, it gives us the Z value. From that Z value we found out the corresponding probability from the table. Now here the probability is given and my Z value is given. That means my say x minus mu by sigma is equals to this psi of this, I get the probability value, right? Now this probability value is given, it is 0.5% or 0.05%, 0.05. This is given. And what I know this x is 25,000. But I don't know mu, I don't know sigma. Similarly, this is also given. This is also same, x minus mu by sigma. This is also 5%, 0.05. I know just x, I don't know mu, I don't know sigma. So two equations are there. Two equations, two unknown variables. So I can find out the values of mu and sigma, isn't it, by solving these two equations. Now determine the tire reliability at 24,000 miles if wear out is normally distributed. So I have to find out the tire reliability at 24,000 miles. 24,000 miles means it will be somewhere here. First let me rub this, then it will be easier for me to show. this was this, okay, this was 25,000. So I need 24,000 miles. 24, if this was 25,000, so 24,000 will be left of 25,000. So 24,000 will be somewhere here, this value. So I need this one. Reliability at 24,000 miles. So reliability at 24,000 miles, this side it will give me f of t, cumulative failure at 24. So reliability will be, this whole thing is 1 minus of this will give me reliability at 24,000 miles. What is the reliability that, what is the probability that it will not fail, probability of failure free? So it will be 1 minus of this. Same thing, that's the same concept everywhere. So here this is given. So if both side is 0.5 in this figure, what we have seen, this is 0.05, this is 0.05, total put together is 10%. So if this is 0.05, this is 0.05, what is the remaining this? Remaining this will be 0.90. So this value is equals to 0.90. Okay. Now we know what is the probability corresponding to this, we know what is the probability corresponding to this. Then we found out the value of mu and sigma. Okay, from the normal table. Similarly, the same way. Now this one is, we got the value 1.645. Again, as I told you, in the 1.645, it is not in the 1.64 is there, 1.65 is there. How we can get the value for 1.64? Just we will add these two values and divide it by 2 in simple interpolation. So that's how we got this value, and by solving this we could solve this, we could get mu is equals to this, sigma is equals to this. Now simply putting the values for that, for finding f of t, 1 minus psi of f of t, I will get is reliability at 24,000. Simple. Okay. So there are some more problems which I have given a link here. There's more problems if you see, which are, these are problems on Weibull distribution. As I already mentioned in my 13th lecture, that Weibull distribution I will not be discussing in this class, because it is, this distribution it's a bit difficult to understand for people with reliability background. They find it more easier to understand. So industry people, if any industry people or if any professionals who are dealing with reliability or inequality or reliability, if they are interested, they can see the reliability distribution slides also. Already I have kept there, I already mentioned in the class. And if they want to practice any problems, they can also see the problems are here, the link is here. There I have around 2-3 problems, solve problems here. So now, but not only that, any students who are interested, any MTech students, if they are interested, even BTech students who are interested, because Weibull distribution is widely used distribution. It is widely used in reliability and quality studies. So if they are interested, they can go through the problems as well as the concept which I have given in my 13th lecture. And any doubt, of course, I will take up in the doubt clearing session. Okay. So it's, but I am repeating, it is not included in the course. That means questions, when I will be setting questions for exams, question will not come from this portion. You can be assured of that. So, okay. So now, here we have almost come to an end of this tutorial classes. Now, by solving so many problems, by now I think you could understand why we need probability distribution. So I thought I should ask this question at the end of this class. We have done many problem and probability distribution. So by now I am sure all of you could answer, all of you could get it, why we need a probability distribution. So from this, from the type of problems we can solve, don't you see that if a probability distribution is given, then from the probability distribution we will be able to find out probability of occurrence of certain values. Suppose the weight of students, weight of child in a particular locality, suppose weight of child in a particular locality, weight of child of certain age in a particular locality, suppose in the age of say 15 to 20 in a particular locality, the weight of the children is, suppose its mean weight is say 40 with a standard deviation of say some x, whatever may be the standard deviation. So now if I am interested, if that means if it is given the probability distribution, here the probability distribution is given, what it is given, we know that it is normally distributed, we know the mean, we know the standard deviation. Now if we are interested, what is the probability that of getting a child of a particular weight, probability that a child of getting weight 30 or 20 or maybe 50 or 60, given the distribution we will be able to tell that. Now the question is that how do we know, given a set of data? First, initially when we are talking about this child weight in a particular area, who told me that distribution? How do I know what distribution it is? I will just have the data. How I will have the data? There are some, I have taken the weight of all the children in that, all I cannot take, I have taken the weight of the few students. Suppose in that areas there are around 1000 children, out of 1000 suppose I have taken the weight of around 1000 children, I have taken the weight. So from their weight, how do I know this weight is normally distributed? So for that there are again different techniques which I will not be discussing there. So given this set of data, so from this set of data we can find out this set of data falls in which distribution. Okay, and there are different techniques for that. One of the techniques is the probability plotting. There are many such techniques from the set of data. So first step is that we have the data. From the data we come up with the probability distribution. Again from the once we have the probability distribution, again from the set of data itself, by parameter estimation we can estimate the parameters. That means what are the parameters? If it is normal, my parameters is mu and sigma. If it is gamma, my parameters is alpha and beta. If it is exponential, my parameters is only beta, or I can say lambda also, whatever I can say. So once we know the distributions, then the parameters are estimated of the distribution. So we have the distribution, we have the parameters of the distribution, we have all the information. So any probability for that we can find out from this distribution. That is basically a useful application of probability distribution. So we are learning probability distribution mainly from this application perspective. Okay, or not only in reliability studies, in any studies, in any analytics, in any business decision, anything, we will have quite a quite application of this probability distribution. Okay. So these are the questions for which I will not be solving for this reliability problem, I mean for Weibull distribution, and then I will conclude this tutorial class with the references, and thank you guys. So next class we will start a new topic, a very interesting topic, that is sampling distribution. Okay, thank you.